we learned these two important limits right here. The two important limits were, you just have the limit as x goes to a, you can just plug in a for x. And the second important limit was, if you have the limit of a constant function, it doesn't matter what the x values are, the y values will just be that constant function, okay? So our plan is to take a expression and break it up into different pieces so that we're just left with those two important limits. So we have a sum law, we have a difference law, we have a constant multiple law, a product law, a quotient law, a power law, and a root law. And on the video, I took this relatively simple looking linear function. This looks like a line, right? It's like y is equal to, and then here's a slope, and here's the y-intercept. And I broke this guy up into pieces until I got those two basic limits that I had mentioned in 1.5. Okay, so that's what we did earlier there. So what we want to do, what I want to do with you now is I want to do this more complicated version right here. So here's something actually that's kind of important. When you look at this expression, it's actually important that you can identify what the fundamental operation is. Is the fundamental operation addition, subtraction, multiplication, division? Which one of those four would you guys say it is? You could type your answer in the chat box or unmute yourself, but what would you say this is fundamentally? Anyone? Addition, subtraction, multiplication, division. Luciano says division. Do we agree with that? I agree with that, Luciano. Thank you for contributing. The reason why it's important for us to be able to recognize that this is fundamentally division is because later on, we're going to calculate the derivative of this thing. We really need to know what rule we should use. So if it's division, you'd have to use something called the quotient rule. So we're going to use the quotient law in this case. And all that says is your limit splits into a quotient of limits. So we could write it like this. 2x squared plus 3x minus 4, and then x cubed plus 1. Okay. So thank you, Luciano. That for sure is our first step, I guess. And then once we do that first step, now we want to break up the numerators and the denominators. So when I look at this numerator over here, I see two operations, right? I see addition and I see subtraction. So let me make a comment. So we use the quotient law first. Okay. And then for our next step, we're going to split up the numerator. So the numerator is going to be the limit as x goes to 2 of 2x squared plus the limit as x goes to 2 of 3x minus the limit as x goes to 2 of 4, all divided by the limit as x goes to 2 of x cubed plus the limit as x goes to 2 of 1. Okay. So what we did there was we used the sum and difference laws. Is there any question about that? No questions. Okay, cool. So then what law do you guys want to use next then? What law do I want to use on this piece or this piece? Any thoughts? You can unmute yourself or type in the chat box. If you look at these different laws here, which one do we want to use next? No one?
Power law?
we can use the power law on one part. So for this term right here, I have a 2 times it, so I could pull out the 2, I could pull out the 3. So Luciano had mentioned the constant multiple law, and I would use the constant multiple law on those 2 pieces. And then Cynthia, you're saying power law, I can use the power law on this piece right here. So maybe I'll do that. Okay. So then my next step here, I would write, this is going to be 2 times the limit as x goes to 2 of x squared plus 3 times the limit as x goes to 2 of x minus the limit as x goes to 2 of 4, all divided by, and you know what, I'm gonna save the power law for the next step, Cynthia. So I did like your answer because I could use it on the bottom here, but let me just save it for the next step because I could use the power law more than once. So so this guy is going to become x cubed plus the limit as x goes to 2 of 1. And what we used there was we just used the constant multiple law. Okay. And then finally, we can use the power law. So we're going to have 2 times the limit as x goes to 2 of x, and I have quantity squared like this, plus 3 times the limit as x goes to 2 of x minus the limit as x goes to 2 of 4. And then in the denominator, I'm going to have the limit as x goes to 2 of x cubed plus the limit as x goes to 2 of 1. Okay. So let me move this over here because I'm going to need to simplify this. Any questions so far? So I want you to see something. I want you to see that now I have the limit of the x guy. And now I have the limit of the x guy here. And I have the limit of the x guy here. And I have the limit of a constant here, and I have the limit of a constant here. So this is just exactly the situation that I can apply right there. In other words, for all the x's, I can just plug in the a, and for all the constants, they just stay constant. So when I go to simplify this, what do I get? I'm going to get 2 times 2 squared plus 3 times 2 minus 4 divided by 2 cubed plus 1. Okay. Is there any questions about that so far? So when you simplify this, you're going to get 10 over 9. So let's highlight that. It's going to be our final answer here. So after going through this ordeal, you guys are probably like, man, this sucks. Do I need to do this for every single problem? The answer to that question is no. We need to do it once, like in this example 1 here. Or maybe on your homework, they might have some problems where they ask you to break it apart like this. I'm not really sure. But we have a theorem called the Direct Substitution Property that's going to make our life way, way, way easier. Okay. So what this guy says is, it says, if you have a polynomial, and this guy up here is a polynomial, or a rational function, and a rational function is a polynomial over a polynomial, right? This is a poly divided by a poly. So this example right here is a rational function. You know, as long as this number a is inside the domain of f of x, then you can just plug in the number. So you don't have to break it up into 10,000 steps like we did over there. You can just substitute the number in, and then the output is whatever the output is, that's the limit. All right. So that's great news for us. So just as a quick question, just or a quick reminder, what are the two ways that the domain can fail? Does anyone remember what the two ways something can go wrong as far as calculating the domain goes? What's one thing we definitely don't want? There's really two of them. Anyone? Any thoughts? 0 in the denominator is 1, Kenneth. That's right. 0 in denominator. Does anyone know what the second one is? It involves like a square root or a fourth root or a sixth root or an eighth root. So, when we write something like this, that's called the nth root. And if n is even, like a square root or a cube root or a fourth root, then x cannot be negative. Okay, so those are the two ways that number would fail to be inside the domain, right? So if you looked at the graph of the square root graph looks like this. So it's defined for positive x values, but it's not defined for negative x values. So these are the two, these are the two main situations we have where something goes wrong in the domain. Okay. So let's take a look at example 2 real quick. When I take a look at example 2, this is a rational function because it's a polynomial divided by a polynomial. And I can see that the denominator is never going to be 0 because it's x squared, which is a positive number, plus 1. So there's no way we can get a 0 here. So that means I can just take this 2, I can just plug it in using the direct substitution property, and then I can evaluate what that limit is easily. All right. So so this would just be equal to 2 cubed minus 3 times 2 plus 1 divided by 2 squared plus 1. So when I simplify this, what do I get? I'm going to get 8. 8 minus 6 is 2. 2 plus 1 is 3. 3 over 5. So that's our answer. So it's much easier than breaking it up into 10,000 pieces. Direct substitution property does not work when we have a 0 in the denominator. And the second situation is when you have a negative number under an even indexed radical. Okay, so the way we write that is we write it like this. We write like this. This number right here is called the index. And this is called radical form. And a lot of times in calculus, we want to write it like this. This is called exponential form. So we got radical form. And then this is what we call exponential form. Does that make sense? Is there any questions for people? All right, cool. Awesome.